from like a value of H equal to 10 to 1000. But then if you're faced with that, then although I have this configuration, what I'm getting is that a H range that's so large. Which H should I be using? So the right thing to do over there is actually to conduct an experiment to find out what is that H value. So normally H is not given to you in real life when you go to the industry. It's something that you need to conduct an experiment to find out specifically for this setup, what is my H value? What is my convection coefficient? Your lab is going to come in week 8. Will be all about finding out, conducting an experiment to find out the typical H value of that setup. So we'll be seeing how to do this experimentally. Now this area here refers to, again, where heat is transferring out perpendicularly. So that's surface area of this solid. And the other T here refers to Ts minus T infinity. Now if I were to give you another case, same kind of setup, same kind of flow out there. I call this Ts. And out there in the infinity, there's T infinity. This is my solid surface. And I say T infinity is actually greater than Ts. Now what does that mean to you? T infinity greater than Ts, what that means is that your surface is actually colder than an ambient. If your surface is colder than ambient, where do you think heat is transferring? Upward or downward? It's going to transfer downward. In that way. That's the direction for heat. And if you were to set up that Newton's cooling law, you wouldn't be using Fourier's law. Fourier's law is mostly for solid. You have, in this case, a convection phenomenon. How do I see a convection phenomenon? Because I can see fluid flowing over a surface. That comes with convection. If you have convection, and if this surface is colder, your heat transfer rate, Q, will be equal to HA, and in this case, equal to T infinity minus Ts. So what I'm saying here is that you got to look at the set of problems that's given to you. Which one is hotter? Which one is colder? If you're required to find out what is the convection, that temperature difference, you got to always take the hotter minus the colder one, or higher temperature one minus the lower temperature one. Okay. So this is a case where the solid surface is cold. So just now when we were saying, talking about the Fourier's law, the Fourier's law has the thermal conductivity that's given by K. What's the units for K? The units for thermal conductivity is that wasn't intelligent answer. Yeah, some that I heard. How about what's the unit for H? The unit for H is given over here. Watts per meter squared Kelvin. It can be watts per meter squared degree Celsius as well. Alright? The Kelvin or degree Celsius at the denominator does not change that physical value. So if I have 10 watts per meter squared Kelvin, it's actually equal to 10 watts per meter squared degree Celsius. The same. Why is it that they are the same? That's because you're looking at change in the temperature. The change of temperature for degree Celsius is actually the same as change of temperature in Kelvin. I know Kelvin and degree Celsius, they are different units, but we're talking about change in what I want to say is that the convection coefficient, that is H, unlike K, is not a physical property. It doesn't mean that, well, for K, it's kind of quite easy to understand. K, thermal conductivity, it talks about how much is resisting, how well can it conduct heat. That's the physical property of the solid. But for convection, when we talk about H value, H is actually not a physical property of that fluid. It's not. It relates to the properties of the fluid and also the nature of the fluid flow. What does that mean? If I have convection across this surface, that convection, that flow is actually flowing faster. Properties of fluid stays the same, the temperature of the fluid stays the same. I know the velocity change because it has to flow faster. The viscosity of the fluid stays the same. Just by mere fact that the fluid is flowing faster, you will have H value at a larger value. So it actually depends on your configuration. Another example is based on what kind of setup that you have. So I can have flow that's flowing across here. And if I were to turn it this way, having the same flow that's flowing across here, my H value is actually different. Just because of this configuration. And H actually is very sensitive to all these changes in orientation, surface roughness as well, the flow properties, how fast it is. So all this will actually change the value of H. So your H is not the physical property of that fluid that's above your solid. It's not that. It's not a thermal physical property. So Glasgow gave you a song. You want to hear that song?
Grace.
Yeah. Next year I'll try to sing, yeah? I haven't got a chance to learn how to sing. That's it. Okay, if you're interested in that song and that can become a YouTube, just simply copy down this part over here, or just type in key transfer song. By the way, the maker of this song has got a few more songs related to key transfer. So you could really, get it inside all these concepts of conduction, convection, and convection. Okay, let's have a look at a topic. Velocity profile. Let me start this by saying how we go about doing the setup. The setup is that we have a plate. Right? This plate is stationary. The plate is not moving. And outside the plate, this is what we call the leading edge. The leading edge is kind of like a knife edge. So it has some depth that is into this screen over here. So there's this background flow, laminar flow. Over here is a laminar flow. Laminar flow just means that it's not turbulent. The flow is kind of streamlined. And it has this velocity and temperature, T infinity and U infinity. That's your background flow. As it approaches your stationary plate, something is going to happen. The velocity that's nearest to the plate, the velocity of that, say, water, the velocity of that water particle that's nearest to your plate, just right above that plate, that velocity, as it comes to that velocity, will be zero. How do we imagine this? If that velocity is not zero, that means your plate will be moving. That's what it's having that molecule moving at a certain velocity. It's at a very molecular level. So that velocity that is on right next to that stationary plate, that velocity of that water molecule will be zero. We can understand that. That velocity that's out there in the T or the U infinity, that's the background flow. That velocity is going to be U infinity. So as you get closer and closer to this surface, you could see that if this velocity is zero, it's going to shear the next layer of the water molecules. It's going to shear it. You have one side that's zero, there's background flow, so that one would be at a slightly higher velocity than zero. The next layer on top of it will be at a slightly higher velocity, and then it kind of like stack up all the way to the top, where this layer up there would have the velocity that's U infinity, that's your free stream velocity. And that's in meters per second. So if you look at it, can I hence draw a boundary layer to encompass that kind of shearing that's going on in there? In this set of notes, it used the word viscous. The fluid would have certain viscosity. So because of the viscosity, if one molecule that's right next to the plate is not moving, then there's certain shearing viscosity is happening in the next layer, followed by next layer, next layer, next layer, that way. So if I were to sketch out velocity profile, this part here, this velocity got to be zero. And increasingly, the next layer would have a higher velocity until it reaches that, what we call the velocity boundary layer. At that velocity boundary layer, where if I were to slice this, right, in this axis, if I were to slide this over here, and have a look at the velocity. This velocity profile is going to be that way. Up to this point over here, where anything above it would be the same velocity of u infinity. That makes sense. So the velocity over here, due to the shearing, it reaches 0, and as you increase up to that velocity boundary layer, then that velocity is going to be the same velocity as this thing over here, u infinity. So now let's have a look at this sigma here. Now sigma is actually called your velocity boundary layer. So let's see over here it is. Velocity boundary layer. It's written only boundary layer thickness. So it's actually your velocity boundary layer thickness. Now the interesting thing is this part over here. What is this one talking about? This u represents any velocity, any one such velocity within the boundary layer. So one such velocity, u. We know that this u would be equal to 0 at when y is equal to 0. So y-axis is over here, and y-axis at the 0 point over here, that velocity is equal to 0. Right? So that velocity is equal to 0. And we know over here, where your velocity at y is equal to your boundary layer thickness, so that is given by sigma, that one gotta be equal to u infinity. Right? Because anywhere over here, these are all your velocity boundary layer, and it's given by the symbol sigma. So now, if we ask ourselves, where is the point that we consider that the velocity in this, the velocity within that boundary layer thickness, when is the point that we consider that it's equal to free stream velocity, u infinity? Because that's the point that we want to sketch our velocity boundary layer. This line over here, this line, is what we call our velocity boundary layer. And sigma is velocity boundary layer thickness. So that's the thickness of that boundary layer. So the point to consider, where is my velocity boundary layer, says that if u, any point of velocity over here, if u is equal to 99% of u infinity, I take that point to be the point where it signifies my boundary layer thickness. Why don't we take u equal to u infinity? Well, that's because we want to consider that at 99% of u infinity, 99% of u infinity, that's where I consider that is my boundary layer thickness at this slice over here. So if I have another slice over here, this will be my boundary layer. This is my velocity profile. It's going to go up here, and then this will be u infinity. I'm not trying to scale them. It should be the same length, same magnitude over here. So over here, it's still going to be 99% of u infinity. Okay? So if I were to readjust this formula, u over u infinity, that would give me 99%. That's what this is showing. Okay? go for a quick break, right? Back by 3:05.